Next process is adiabatic process, and it is one of the important process. Adiabatic process is the process in which there is no exchange of heat, that is dq equal to 0. And practically we can say a process which takes so fast that there is no time to exchange the heat. That process is the adiabatic process. And using the first law of thermodynamics, where we know that dq equal to du plus dw, that is change in heat equal to the change in internal energy plus work done. And here for adiabatic process dq equal to 0, so we can write du plus dw equal to 0, hence dw equal to minus du. If we consider the adiabatic expansion, and we know for expansion work done is positive, work is done by the gas or the system. Therefore, in this case, the change in internal energy will be negative. So we write du is less than 0. If we consider this equation du equal to minus dw using the first law of thermodynamics, it means that this du is n Cv dt, where n is the number of mole of the gas, Cv is the molar specific heat at constant volume, and dt is the change in temperature, and it will be equal to minus Pdv. Hence, n and this Cv is R by gamma minus 1, and remaining is dt minus Pdv. So this implies that nr dt can be written as minus gamma minus 1 Pdv. And using this dRt in equation of the ideal gas, because we know ideal gas is the PV equal to nRT, and on differentiating we will have dPV equal to dnRT, and differentiating this we will write PdV first function differential of second plus second function differential of first, and nr is constant, so it is taken out of the integral and remaining is dt. And here we replace this nr dt from the value calculated above. We will have Pdv equal to plus Vdp equal to minus gamma minus 1 Pdv, and on expanding it, it is minus gamma Pdv plus Pdv, and this Pdv get cancelled, so we write Vdp equal to minus gamma Pdv, or we can write it as dp by p equal to minus gamma dv by v. And now on integrating this, we will have integral dp by p equal to minus gamma is constant, so it is taken out of the integral, and it remaining is dv by v plus a constant, which is the constant of integration. And integral of 1 by p is log p, and it is equal to minus gamma, and dv by v is also log v plus k, and this side to taken on the left hand side, this is log p plus gamma log v equal to k, and we can write it as log pv gamma, because this gamma, if we bring inside the log, it becomes in the power of the v, and because this log p and remaining this another log v are in addition, so they will multiplied in the argument of the log. So it is p v power raised to power gamma, and it is equal to k, and this k we can replace in terms of log, that is log c. C is also a constant. Hence we can write p v raised to power gamma, that is equal to a constant term, and it is a very important formula for the adiabatic process. So from this dp by p equal to minus gamma dv by v, we calculated dp pv raised to the power gamma, that is equal to constant. And if we replace from the ideal gas this p equal to nRT by v, then we will get this formula. This can be calculated as nRT by v into v raised to the power gamma, that is equal to constant, and this implies that t into, because n and r are constant, so it is they are taken in the right hand side, it becomes constant also, so it is t v raised to the power gamma minus 1, that is equal to constant. Similarly, we can calculate the relation in terms of the t and p by replacing the v equal to nRT by P, and we will get T raised to the power gamma into P raised to the power 1 minus gamma equal to constant. So we have very important relation that for adiabatic process that PV raised to the power gamma, it is a constant, or we can also write TV gamma minus 1, it is a constant. Similarly, one of the another relation is T raised to the power gamma, P raised to the power 1 minus gamma, that is equal to constant. Here P is the pressure, V is the volume, and T is the temperature of the gas, where gamma is the ratio of the molar specific heat at constant pressure and constant volume. This is Cp by Cv. If we compare the graph of the isothermal and the adiabatic process in respect of their pressure volume graph, we see the slope of the adiabatic process is more or a higher slope, while the slope of the isothermal process will be lesser. Here we have written that slope of adiabatic curve or the process is more in magnitude in comparison to the slope of the isothermal curve. So many times question is asked on the basis of this graph. Therefore, we should remember that lesser slope means isothermal and more slope, magnitude of the slope, more magnitude of the slope, that is the adiabatic process in the PV diagram. Because for adiabatic process we know PV gamma, this can be calculated mathematically also. Because PV gamma is constant for a adiabatic process, then on differentiating first function, differentiating the second function, that means V raised to power gamma. So this is the coefficient gamma, and this V raised to power gamma minus 1, and then differential of this variable V, plus then second function and differential of first, and because constant is on the right hand side, so differential will be 0. Now we calculate the magnitude of dP by dV. This is the dP and this is dV. So dP by dV for the adiabatic process, this relation is adiabatic process, so we are getting the value of dP by dV here for adiabatic process, and this will be, because here it is V raised to power gamma and here is V raised to power gamma minus 1. If we cancel this, so we will left with V, and here it is P. So we will simply have, if we bring this term as V gamma dV equal to minus V dP, or dP by dV equal to minus P by V into gamma. If we take the magnitude of dP by dV, so it will simply gamma P by V. And this P by V is the slope of the isothermal graph, which we can calculate from the ideal gas equation. It is PV equal to nRT, and where for isothermal process this T is constant. T is constant for isothermal process. If T is constant, then on differentiating this P first function differential of second plus second function differential of first, and this whole term nRT is constant, so its differential will be 0. And now from this equation we can write P dV equal to minus V dP, and this equal implies that dP by dV equal to minus P by V. So if we find the magnitude of this dP by dV, that is the slope of the isothermal graph, we will have dP by dV magnitude for isothermal graph, that is equal to P by V. So this P by V is the slope of isothermal graph. Therefore we can say this dP by dV for adiabatic process, that means slope of the adiabatic process is equal to the gamma times of the slope of the isothermal process, and gamma is always greater than 1, where we have already mentioned that this gamma is the specific heat ratio at constant pressure and constant volume, and we know constant pressure, specific heat at constant pressure is always greater than Cv, so this implies that gamma is always greater than 1. Hence slope of the adiabatic process will be more than the isothermal process.